Distortion in weldment also consequence of the residual stresses developed during the welding process, but the main reason for the distortion in the weldment structure is mainly the solidification shrinkage, any thermal contraction, and of course, metallurgical changes also happens during the welding process, and if there is any boundary constraints, all this actually influence the distortion in the final weld joint structure. So, the reasons for the distortion in weldment is very similar to the reasons for the generation of the residual stress in welding. So, that is why always we usually used to say that distortion and residual stress in welded structure, they are linked with respect to each other. Now, how we can measure or how we can quantify the distortion in a weld joint. So, if you look into try to do some butt joint configuration, then main straightforward way to measure the specifically the angular distortion during the welding. So, angular distortion can be measured even for the welding of the very thick plate or maybe welding of the very thin plate. So, figure shows that first figure the transverse shrinkage in a butt joint configuration, that transverse shrinkage if it can be a concave or convex type of buckling also occur within the welded structure depending upon the types of materials. And if you look into that figure the angular change in a butt joint. So, simply assuming the along the longitudinal direction the plate is very straight and there is only the angular distortion, and that we can measure it, or angular change in the T joint may also happens during the welded structure, and longitudinal direction in a fillet joint also it bends or buckling may happens corresponds to the kind of convex kind of structure. So, depending upon the whether the distortion is with can happen in a concave type or convex type or maybe straightforward simply angular distortion, all can be measured in straightforward using probably we can use it simple coordinate measuring machine or some laser scanning system. With respect to some reference point we can measure the distortion. But what is the reason for this generation of the distortion? The welded component basically can shrink in the different direction depending upon the weld nature of the type of the weld joint, and that means both transverse as well as longitudinal direction the deformation may also happen. So, buckling may also happens, and accordingly we can classify the different types of the distortion in a welded structure. Here if you see that right hand side the figure indicates the actual the joining of the titanium alloy using the plasma micro welding process, and here only the thickness of the plate is 0.5 millimeter. That means it can be considered as a joining of very thin sheet. So, in this case we can see that the deformation is the concave convex type depending upon which and whether we are looking in the along the transverse direction or whether we look into the along the longitudinal or welding direction. So, in this case it is wise to measure the distortion not in terms of the angular distortion, but more accurate measurement of the distortion can be done if we locate the several points on this weld, and then if we try to measure the different point probably we can measure the distribution of the distortion at the throughout the whole structure. But it is a simplified way we can measure only on the angular distortion. So, with respect to the initial position and after the butt welding what is the distortion of the plate happens, and that can be measured in terms of the D as shown in the figure. So, this is the way to measure the distortion, but what way we can reduce the distortion, because this amount of the distortion is a very serious problem in the welding process, and this actually creates the dimensional accuracy when two different components we are trying to join this. So, there are several ways to reduce this amount of the distortion. One is that by reducing the weld metal volume. So, that means melting volume of the material, if it is less amount then probably we can reduce the distortion. Of course, in this case the less amount volume, less amount of the molten pool volume, but at the same time it should attain the full depth of penetration. In case of using electron or laser beam welding, the maybe the solution, because in this case the oil pool volume is relatively small as compared to the other gas or arc welding processes. So, therefore, laser welding or electron beam welding is the one solution to minimize the angular distortion or other kind of the distortion in welding process. Placing welds above the neutral axis, if you when you try to do kind of V joint kind of this thing. So, there is a the volume of the welding pool metals not this is a not uniform throughout the depth of penetration structure, it varies from maximum to the minimum point. So, with respect to that type of cross section, if it is possible to place the equilibrate amount of the oil pool volume with respect to the neutral axis, then probably in that case that the amount of the distortion can be reduced. And of course, one very large structure or maybe in a very complicated, that following the multipath or multipass welding process, the distortion can be controlled. So, multipath means if you use the laser scanning or using the laser welding throughout the structure and following some specific pattern of the scanning of the laser on the surface, and the path can be different. So, designing the path, probably we can reduce the amount of the distortion, or sometimes in case of multipass welding, not placing the or supplying the molten material within the oil pool volume, not only on the single pass. If it can be filled by using the several passes, probably in this case the amount of the distortion can be reduced, and this multipass welding process mainly happens very high thick material. So, these are the very straightforward way to reduce the distortion of the different welded structure. Now, other type of methodology also exists to reduce the amount of the distortion. If we simply look into this figure, that presence of only single V, that means one sided, and welding of this thing can definitely most of the cases it will produce some angular distortion. Specifically, the angular distortion is mainly happens when the thickness of the plate is relatively high, and in this case, if the similar kind of similar kind of oil pool volume can be placed in the both sides of the plate, then it will try to neutralize the amount of the angular distortion, or it can be reduced the amount of the angular distortion, and it is very obvious from this the figure. So, therefore, welding alternately on the either side of the double V joint is preferred to reduce the distortion. And another mechanical way to that, by using the elastic pre-spring before the welding, can also helps to reduce the angular joint. That means, simply that before welding some angular, intentionally you could give some angular distortion, and if you do the welding joint, so that after welding it can try to neutralize the pre-existing angular distortion of the weld joint. So, that is the one way to reduce the distortion. Definitely preheating, sometimes the preheating of the material before welding can also reduce reduce the distortion. Thermal management during welding, that means it is possible to control the thermal cycle, that means time temperature cycle during the welding process, that also influence the distortion level of the weld joint. And of course, post weld heat treatment or post weld heating also sometimes reduce the angular distortion. So, that means it is a very straightforward way using some mechanical means, for example, pre-straining or pre-springing angular changes can reduce the distortion, but at the same time the distortion also affected by the some metallurgical changes, and that metallurgical changes is very much influenced by the thermal cycle in the welding process. Thermal cycle means the time versus temperature cycle. So, by proper control of this time versus temperature cycle, or we can say the thermal management of the during the welding process, that helps to reduce the amount of the distortion. Apart from that, preheating or post heating also helps to reduce the distortion level simply by changing by the microstructure of the weld joint. So, these are the typical methods for reducing the distortion level in a welded structure. Now, we come to that point that one significant or important part, that is the welding solidification in welding process. So, definitely the molten pool with when come in contact with the some cooling medium, and most of the cases is the open atmosphere, and that or it is also sometimes under the shielding gas, or maybe in sometimes it can be done in a closed chamber also. So, anyway, some kind of cooling medium exists. So, the molten pool gradually solidify and come back to the ambient temperature, or maybe come back to the service temperature. So, that during the cooling period, the what is the thermal cycle, time temperature cycle, and what is the rate of cooling, that is very much significant or important in the solidification process of the welding in any welding process. So, because the solidified structure is actually decides the mechanical properties of the weld joint. So, it is very much necessary to understand the solidification behavior in welding process. Now, there are several solidification theory, but our focus is only in specific to the welding process. So, here if you see that mode of the solidification, that what is the final shape and size of the welded microstructure, that can be said that mode of the that depends on the mode of the solidification. So, therefore, temperature, the solidification happens, the temperature of the weld pool comes from superheating temperature to the phase transformation temperature, basically solid state phase transfer from liquid to solid phase transformation temperature, and then gradually cooling from that solid gas temperature to the ambient temperature. So, throughout this process there may be the several phase transformation may occurs, and specifically that phase transformation not only the liquid to solid phase, but in case of alloy there is a solid state phase transformation may also occur. Now, if we look into that typical the time temperature curve in solidification process, if we look into the specific pure metal, we know the basic elementary curve for the time versus temperature. So, first curve is first figure is shows that in case of the pure metal, when you try to follow the cooling from the some superheated temperature, and then when it comes to the melting point temperature, there is a some time lag, or maybe some time is required to change the phase without changing the temperature. So, that melting at the melting point of the specific pure metal. So, specifically in case of the pure metal, there is a single point there is a single melting point temperature. So, that means the from liquid molten pool to the solid material may happens over single temperature, but over a lapse of time. So, that lapse of time is basically the release the specifically a latent heat by changing the phase from liquid to solid phase. So, that graph clearly shows that there is a phase change over time, and from liquid to solid, and gradually in the solid state there is a considerable decrement of the time. So, this is a typical solidification curve in case of the pure metal. But if we look into that cooling curve of the alloy system, so in this case specifically the alloy system, or it is easy to explain the alloy system if we consider the binary alloy. So, in this case the time versus temperature, if we see that it starts from the superheating temperature, and one that is a liquidous temperature, and there is a two defined temperature over which the solidification happens. That means, from between the liquidous temperature to the solidus temperature. So, between these two is normally called the Mushy zone. So, the mixing of the solid and the liquid phase exists between these two temperatures, solidus temperature and liquidus temperature. So, like pure metal, the phase transformation from liquid phase to the solid phase does not happen on a single point temperature, rather it happens over a range of the temperature. So, within this range of the temperature, of course, the phase change happens from liquid to solid phase, and these are the typical cooling curve or time temperature cycle in case of alloy material, alloy system. So, with this basic understanding of the cooling curve, we will try to explain the solidification behavior of the in case of the welding process. Now, more intuitively, if we look into